So last Friday, we started on this topic of transient conduction. So who knows what the word, who can explain what the word transient means? Okay, yeah, changing, or in mathematical terms, we do not neglect the accumulation term in the heat equation. So we have to account for how things are changing, and specifically this term helps us track how our temperatures are changing with time, and really how energy is being stored with time. So we introduced this method, the first method and the simplest method for dealing with transient analysis of conduction is called the lumped capacitance method. So what's the key assumption we're making when we're using the lumped capacitance method? Yeah, Blaine? Great. So he's saying, yeah, heat transfers through the solid fast enough that you don't have any difference in temperature from the boundaries into somewhere in the center of the material. That's perfect. So basically we're neglecting any change in temperature with respect to our spatial coordinates. So I'm showing the slide that has the heat equation, and when we're making this approximation, we are pretty much scrapping the heat equation almost entirely. So we're going to replace this whole left-hand side with just a simple energy balance of our entire solid. So it's really no longer the heat equation at that point. So we talked through when we can do this. So for a general energy balance, we'd have our accumulation equals, we would leave a placeholder for some source flux at a boundary. We'd have convection. We could also have radiation, and then we could have a generation term. So we can certainly get into more simplifying assumptions. So we specifically went through when there's just convection. So we're neglecting any other source of thermal energy, any other flux at the boundaries. We're neglecting any generation, and we're neglecting radiation. So we're just left with our accumulation term and then this convection term, which would follow Newton's law of cooling. So we went through and derived this equation. The math really wasn't that bad in this particular case, and we ended up seeing that our temperature dependence with respect to time is going to be exponential. So if we have our initial temperature here of our solid, and we have time on the x-axis, and then we had some T infinity here, by plugging in actual numbers into that equation, we would see that our solid will exponentially approach the ambient temperature until it reaches thermal equilibrium, and it just stays there being equal to the ambient temperature. So that's basically what that equation tells us. Okay, so there are other cases. When you consider radiation, the math gets a lot trickier and kind of uglier because you pick up all these extra nonlinear terms. But then we got to the specific set of circumstances for when you can apply this lumped capacitance method. So specifically, we defined this Biot number, and I remember I went through this fairly quickly to get everything crammed in time, but we're going to go back and review this a little bit. So the definition of the Biot number is, it's defined as H, which is our convection coefficient, multiplied by L sub C, which is a characteristic length of our solid. So that characteristic length is given by the volume divided by the surface area. And then we have those two things are both divided by K, or the product of H and L are divided by K. That gives us what's called the Biot number. So this Biot number is a dimensionless number that we will use to determine whether we can apply the lumped capacitance method or not. So when the Biot number is really, really low, much, much less than 1, then we could say, okay, the lumped capacitance method would apply. That would be a good approximation in that particular case. So if we're thinking about, if we want to get some physical intuition, so systems that would have a really low Biot number would typically correspond to systems that have a really high thermal conductivity. So think of metals, or systems that have a really low convection coefficient, meaning that convection happens so slow that conduction happens relatively fast compared to convection. Yeah, Donovan, did you have a question?
Yeah, so for, say, much less than 1, is that kind of like 0.1 or more like 0.2?
Yeah, 0.1 is a pretty good rule of thumb. Yeah. If it's somewhere in the neighborhood of 1, then maybe it's an either or kind of a situation. We'll have some examples later in today's lecture to help you guys get a little bit of intuition. So, and just remember, this is a simplifying assumption. It's an approximation. So part of that would depend on how much do you care about knowing the temperature profile versus a spatial coordinate. So if that is really not that important to you, then maybe a BO number of 0.5 would be okay. But if you really care about how temperature varies with space and time, then you'd probably want to get a more rigorous solution method. So one way to think about the BO number is that it is the conductive resistance to heat transfer divided by the convective resistance to heat transfer. So if you remember, when we talked about thermal resistances in series, I strongly cautioned against using these thermal resistances unless the system is at steady state. So, however, they can still come in handy in sort of helping us qualitatively understand what goes into the BO number and how fast is one thing happening relative to another thing. So the BO number, you can think of it as the conductive thermal resistance divided by the convective thermal resistance. So if there's very, very low conductive thermal resistance, that means heat's going to propagate through your solid. It's going to conduct through your solid very quickly, making your BO number very small, meaning that you could apply the lumped capacitance approximation to your system. So here are several different examples. So on the far left, this is a BO number that is much, much less than 1. So we start out, here's our initial condition, and this is a system that is undergoing cooling. So you can see that over time, our temperature is gradually reduced, but the temperature profiles still stay relatively flat through this whole process until they approach T infinity. Whereas in the opposite case, well, I guess here's actually a good example to Donovan's point. So maybe a BO number, if it's right around 1, isn't that great of an approximation. You can still see there are some pretty significant temperature gradients there. And then when our BO number is really big, then absolutely approximating this as all being uniform in temperature is not a good approximation. So in our last class, I gave the examples. I try to always have some kind of conceptual example for you to help put these concepts in the math to a real-world example. So the one on the left, this would be a lot like the steel wall. You'd expect heat to propagate through the steel wall really quickly, whereas in the wooden or oak wall, you'd expect to have these much more pronounced temperature gradients in your system. Any questions there? Okay. So we're going to switch over to the second part of this. So certainly I do want to point out that making the lumped capacitance approximation, those end up being a little bit better homework and exam kind of problems because you can actually find the equations, or you could even solve the equations on your own. When we're considering transient conduction, so a change in temperature with time in addition to spatial effects, then solutions get a little bit trickier, although we will have some that are still doable. So before we get too much into that, I've launched a quiz on the Socrative app. And again, remember our room name is POW3453. So we're going to calculate the BO numbers from those hypothetical examples. So for a plain wall made of oak, where K is equal to 0.17 watts per meter Kelvin, we're going to assume that it's insulated on one side, and it has a thickness of 15 centimeters. What is the BO number if the surface to air convection coefficient is 50 watts per square meter? And then same thing for a plain wall made of steel, a different thermal conductivity, but everything else is the same. And I want to point out that L sub C, our critical length, is defined as the volume to surface area. So for a plain wall that's insulated on one side, that's just going to be the thickness of the material. In other words, L sub c is just 15 centimeters in this case. So go ahead and calculate those Biot numbers, and you can answer both questions at the same time now without having to wait for me. So go ahead and plug them in, and we'll see how everyone's doing. Whoops. Yeah. We might want to wrap this up after class, yeah. Sorry. Okay, so I'm going to go ahead and show the answers here. Okay, so pretty good. So the oak wall has a Biot number of about 44. So would you apply the lumped capacitance approximation for the oak wall? No, much greater than 1, so 44 times that. So pretty clear, pretty easy. Then the steel wall, in this particular case, has a Biot number of 0.25. So would you apply the lumped capacitance approximation to the steel wall? There might be a little bit of ambiguity there, but in general, you're probably okay. And I'm going to show some results, actually, and it'll probably assure us that the lumped capacitance approximation would be pretty good in the steel case. So just by changing that thermal conductivity, you can see that the Biot number will change drastically. And that will inform you as to how much of a simplified approximation you can take to solving the system. Yeah, Titus?
Is the temperature you get from the lump capacity kind of equivalent to the average temperature? Is that?
Yeah. So that would more or less equate to an average temperature. Yeah, that's great. Okay, so in the oak wall case in particular, we have learned that while that lumped capacitance method was nice, the math looked really pretty. It was an equation with could probably do some pretty simple plug and chug kind of stuff. So that was really nice and ideal, but we've just learned that for the oak wall, we can't do that, so we've got to find a different methodology for solving for temperature in the oak wall. So we're going to go back now to the heat equation, and we're going to look at this guy. So I really hope you're starting to get a sense of, especially after solving the two-dimensional conduction problem, basically we're just solving a numerical approximation to the heat equation. And even in that case, we simplified 3 out of the 5 terms, and once you solved it, you still got this really nice and intuitive map of how temperature is changing in the solid. So the heat equation is just, by solving it, there's just so much information you can get, except accounting for each of these 5 terms can be really challenging. So again, we're going to reduce the heat equation. So this is still one-dimensional conduction. and we're considering transient analysis. So tell me what terms we can get rid of in the heat equation. Q, great. So no generation. Okay, we're only considering one dimension, so we don't need change in temperature with y or with z. Okay, so we're left with this equation, and if we're assuming constant thermal conductivity, we can pull k out of the derivative, and we can get k times the, still partial, k times the second derivative of temperature with respect to x squared is equal to rho Cp times dt. So this is the equation that we're solving for a plane wall system where we care about how temperature changes with respect to x and how temperature changes with respect to time. So this is a partial differential equation because we have change in temperature with respect to two different variables. I want you to really remember this equation. Just the next several slides, you're going to see some math that gets kind of hairy and kind of ugly, and you might get lost in the weeds. So I want you to come back and remember we're trying to solve this equation. We're specifically trying to figure out how does temperature change with time and with one spatial coordinate by solving the heat equation. So to make the math a little simpler, so the book will go through some lengthy solutions to these equations and deriving how you get the temperature, the transient temperature profile. So they start off by lumping terms. So one of the terms is called alpha, and this is defined as k over rho Cp. This is called the thermal diffusivity. So the thermal diffusivity is a ratio, basically a ratio of how fast heat is going to propagate through a solid divided by that solid's capacity to absorb heat. So if you remember, we called this rho Cp the thermal capacitance of a material, so basically how much energy it can store. So this is the thermal conductivity divided by the thermal capacitance, and it's just a measure of how fast temperature is going to propagate through our solid. And you'll see a lot more lumping of terms here in the next few equations. So if we find out that we cannot use the lumped capacitance approximation, we have to deal with that spatial coordinate. We're fortunate enough to neglect generation and variations with y and z in this particular case, but we still have to solve this equation that the solution to it is actually kind of tricky, and I'm not a PDEs teacher, so I'm happy to just jump to the solution and have you guys use the solution there. So what we do is we go through and we simplify that equation. So if you remember, I just pointed out what alpha was. So here's this simplified form of the equation. Then boundary conditions are going to play into this as well. So when we're solving the heat diffusion equation, for each spatial coordinate, because it's a second order differential equation with respect to that spatial coordinate, you need two boundary conditions. This is also a transient problem, which means you need an initial condition as well. So you need to know, what does my temperature profile look like when I'm starting out? So this T for all x and at time 0 is equal to some initial temperature. In this particular case, we are solving a plane wall system with either some symmetry or insulation. So in this particular case, you have a plane wall, you have convection happening on each side, and T infinity is assumed to be equal on each side. So that gives us this boundary condition that there is 0 flux at the center. So this system ends up being the exact same mathematically as having a half-thick wall that's insulated on one side. So that symmetry means you're going to have a temperature profile that looks like this. So right at the center, our derivative with respect to x is just 0, so there's no driving force for heat transfer, so we have a 0 flux condition at the center. And we also end up needing to just solve 1/2 of this because it's symmetrical. So that's one of our boundary conditions, and then in this particular case, our other boundary condition is a convection boundary condition. So even though this form of the heat equation looks simple, by the time you apply boundary conditions, you pick up some other variables. So in total, you get these 8 independent variables. So we have X, we have time, we have our initial condition, we have our ambient conditions, we have L, which is the total thickness, thermal conductivity, our alpha, and also our convection coefficient. So you can combine these constants and get a solution. So we start out by defining this dimensionless temperature difference, which is the theta star, and that is defined as the temperature of our solid relative to T infinity divided by the initial temperature of our solid relative to T infinity, and it's the ratio of those two things. We also have this dimensionless space coordinate, x over L. So instead of dealing with x equals 4 centimeters or 3 meters or whatever, we just ratio that to the full thickness of the wall, and so we end up with x varying from 0 to 1. We also define a dimensionless time, which is defined as alpha, or our thermal diffusivity, multiplied by the actual time, divided by the thickness of our wall squared, and that gives us this dimensionless time, also known as the Fourier number. So a Fourier number is just a dimensionless time. We have the Biot number, which we've defined before. So we end up reducing our system in terms of these simplified variables. And we solve the heat equation. I'm not going to go anywhere near actually doing the math to solve that. This is what our solution ends up looking like. So it's an infinite series in terms of constants, and this zeta term, which will be defined in a table here in a minute. So the zeta term is the roots to this particular equation, and these constants are given by plugging and chugging zeta into that equation. So again, I don't want to get lost in the trees here. Remember, the bigger picture is we're trying to solve the heat equation to figure out how temperature is changing with respect to space and time through a plane wall. And then we picked up all these ugly little things. I personally think that zeta term, I used to call that squiggle when I was a student. I'm pretty sure that was invented just to freak engineering students out. So don't be freaked out. These are just variables. You can end up doing just plug and chug. So make sure that you grasp the concept. Solving this equation gives us temperature as a function of x and time for a plane wall system under certain circumstances, like when you have a constant initial temperature. So again, this is an infinite, we have an infinite series here. That is our solution. So by going through and doing the nitty-gritty things like figuring out what zeta is and what c is, and our Fourier number, and plugging that into this equation, we would get our theta star, which is just our dimensionless temperature difference. And from that theta star, you can now go in and just plug in the right terms, multiply by the temperature difference, and you can get the actual temperature varying in your solid. So nothing to be freaked out by. And typically, this infinite series, the first term is going to contain most of the information. Then the second term, less information. The third term, less and less and less. So you can get a pretty good approximation here by only including the first few terms. And in fact, only the first term gives you a pretty good approximation to this. And that's typically all that we'll deal with when we're solving these kinds of problems within the scope of this class.
Were you saying that the more terms you add in that infinite series, the less accurate it is?
Well, no, the more terms you add, the more accurate your approximation will be. But you can still get pretty good by making an approximation and chopping off a bunch of those terms. Yeah, so dealing with just one term, it's not perfect. And in fact, it only applies when you have these high Fourier numbers. Well, relatively high. So when you're only after a certain amount of time do those less important terms start falling off, and your one-term approximation becomes pretty good. So there's a table in your book, table 5.1, for those who have the printed 7th edition, where you can go look up what zeta is and what your constant is. Right now we're only looking at the plane wall system. But you can see that zeta and c are both a function of our Biot number. So the Biot number is HL over K, so we can just treat those all as constants. We can go look up our Biot number. Let's say it's 0.25, like in the steel example. We can look up what zeta is. Oops, I went too far. We can look up what zeta is and what C1 is. Then we can go plug these into our equation and solve for our temperature profile. So just to give you kind of a visual on how to do this. So this would be the kind of a nice thing to do in a spreadsheet. So for the steel wall, so this is just really just being detailed and meticulous and trying to keep track of your terms. So the steel wall example, we would just put in our characteristic length, our thermal conductivity, all the different material properties here. This is our initial condition. This is our ambient temperature. This is a calculation of our thermal diffusivity, or alpha. So we'd calculate our Biot number. Based on that Biot number, we'd go look up what C1 and zeta are. And then we can go through and calculate how our temperature changes with respect to space and time. So here's time going down in this column in hours. So we then go calculate what our Fourier, remember Fourier number was a dimensionless time. So as the real time increases, so does our dimensionless time. So based on that Fourier number, our temperature profile is going to change. And then here going horizontally, I've put our x. So this particular example, we're looking at a 15 centimeter thick wall, and we just calculate the normalized temperature here. So now we can go in and plug all those equations in. So this is basically that one-term approximation, just in Excel form. And you can see it references our dimensionless distance, our dimensionless time, and the C1 and zeta, and it also references our initial temperature and our ambient temperature. And then this is me just plotting certain lines through the steel wall. So we started out at, let's see, we started out at 5 degrees C, right? Yeah, our initial temperature is 5 degrees C. So these are solutions at different times. So this is after 1 hour. This is what our temperature profile looks like. The whole wall has pretty much risen above 10 degrees C. Then after 2 hours, now it's all above 15 degrees C. After 4 hours, it's all between 20 and 25. And then after 8 hours, we've reached thermal equilibrium, and we're pretty much, no, our ambient was 30, right? So we're still not quite there, I guess. Yeah, ambient was 30, so we're still not quite at 30 even after 8 hours, but we're pretty close. Yeah, Donovan, did you have a question?
Yeah, so is L in these equations the thickness of half the wall?
It was the thickness of the full wall because we're assuming that the left side of the wall is insulated.
Okay.
Well, oh yeah, actually, this would apply in either scenario. So it could be a 30 centimeter thick wall with convection happening on both sides, or it could be a 15 centimeter thick wall that's insulated on one side. And mathematically, those two situations are equivalent.
Now with this graph, wouldn't we just flip it over to the other side, and that would be the full wall where
Yep.
you have the tiny
Yeah.
hump in the middle?
Exactly. Yeah. So because of symmetry, if this were that doubly thick wall that had convection on both sides, this is just the temperature profile of half. And yep, exactly. So flipping it would just show the other half. Okay. So I want to point out. So the thermal diffusivity, K over rho Cp, in this case is 7.8 times 10 to the minus 6 meters squared per second. If we looked at our thermal capacitance, rho times Cp, for the steel wall, that is 3.8, and I think this would be joules per meter cubed per Kelvin. So just remember that number, 3.8 million for the steel wall. So now let's go look at the oak wall. So same kind of a thing. If you remember, our Biot number, as you calculated, was 44.1. But we do that same kind of an analysis. And now let's look at how that temperature propagates through our oak wall. So you can see, and notice before I was plotting 1 hours, 2 hours, 4 hours, and 12 hours, I think. Now we're looking at much longer time, so 12 hours, 24 hours, 48 hours, 96 hours. So at 12 hours, we see this pretty pronounced temperature gradient, and that is due to this having a much higher Biot number, mainly because it's the thermal conductivity of oak is much lower. So after 24 hours, we're getting higher temperatures. After 48 hours, and even after 96 hours, after 4 full days, this oak wall still hasn't completely reached a steady state yet. Any questions here on how to do this kind of analysis? The math looks a little bit uglier. I'm not going to ask you to go and integrate the heat equation in these cases, but it's important to recognize the particular setup of the problem and to know that you can look up the solution and get this one-term approximation to solve for the temperature profile. Okay, so here's how they look side by side if you're interested. So I do want to stop and ask, or stop and help you think. So for the steel wall, even with the Biot number of 0.25, do you feel pretty good about applying the lumped capacitance approximation to the steel wall? Okay, so still pretty good. In certain circumstances, we might care about, so there is still kind of a temperature gradient here. So maybe for some reason we want to know exactly how that temperature profile looks. But in general, we could just treat these as flat lines. So by applying the lumped capacitance approximation, instead of using this one-term approximation to the real analytical solution, we would lose that information regarding how that changes with respect to x, but certainly losing a lot less information in this case relative to the other case. Okay, so, and I wanted to point out, okay, so the thermal capacitance per unit volume, rho times Cp, for the steel wall is 3.8 megajoules per meter cubed per Kelvin, while the oak wall is less than half of that at 1.5 megajoules per meter cubed Kelvin. So they both have the same volume and are exposed to the same conditions. So notice the steel wall actually has more than double the capacity to absorb heat relative to the oak wall, but still it heats up a lot faster. So why is that? Anyone want to say it out loud? Yeah. Okay, yeah, the rate at which heat propagates through is so much faster. So there's this, while you couldn't use the thermal resistances and series methods explicitly to solve for this because it's not steady state, that idea still qualitatively applies, that the thermal resistance through this steel is a lot lower because it has a much higher thermal conductivity. So even though the accumulation term is a lot bigger for the steel, it's more than double, and specifically I mean the thermal capacitance, it still heats up a lot faster because it has a lot less resistance to heat flowing through it. So the process happens faster because of that higher thermal diffusivity. Any questions there? And actually, if you do, when we went back and lumped all those terms together, so at the end of the day, we're basically just solving this problem. So that relative ratio of K over rho Cp, which is our alpha term, that determines how fast your temperature profile evolves. So when you have a higher thermal diffusivity, then things happen a lot faster with respect to time. Yeah, Donovan?
In Excel, to get those graphs, did you have to use solver at all? Or was it just
Nope. Didn't use solver, that's just plug and chug. Yeah. Yeah, good question. So it's just finding the constants. It's really just an organizational thing more than anything. Keeping track of what all your dimensionless variables are and substituting in the right numbers. On an exam, I certainly wouldn't be able to ask you to plot something like in Excel, but I could ask, what's the temperature at a specific time and at a specific point in the solid, that would be a valid question where it's just at x equals 0.3 centimeters and time equals 4 hours. Then it's a similar kind of exercise, except instead of plotting it or instead of calculating rows and columns to contain all the information, you're just getting information from one specific point. Any more questions there? Okay. Okay, so now moving on to radial systems. This is a very similar idea. You still have the Biot number, although the Biot number is going to be defined differently. So the Biot number is going to be the volume divided by the surface area of your solid, but certainly the same kind of things would apply to a radial system. The solutions are just going to look different. So when we have long rods or spheres heated or cooled by convection, our Biot number is now going to be H times R over K, and that can vary depending on how you're defining your critical dimension. We can talk about that later. And our Fourier number is a little bit different, but we're still basically solving that same form of the equation, except now we care about the term that has dt dr in it instead of dt dx. So you can get these one-term approximations again. You can look those up in the book. They are equations 5.52 and 5.54 for the long rod or a cylindrical system. And then for a sphere, they are 5.53 and 5.55. And you can look up these constants in some different tables. Again, I hope you're just grasping sort of the idea of this whole thing. So for an infinitely long cylinder, this is what our solution looks like. So now we have a new term, which is this J naught. This is something called the Bessel function, which I'll define later. And we can certainly just take the first term of that infinite series and get a pretty good approximation for how temperature evolves with respect to R and time. So breaking down each of these terms, so remember our theta star is just that reduced relative temperature. That constant C1, you can look up in the table that we showed previously. We have the Fourier number, which is defined as alpha times time over our radius squared. This J naught is a Bessel function of the first kind. This is just a function that comes up when you solve differential equations of this form. Again, we have our zeta constant from that same table, and now we have our dimensionless radius. So it's just plugging and chugging, making sure we're keeping track of each of these terms. Then what we actually solve for is this relative dimensionless temperature, and you can just back solve to calculate what the actual temperature is based on that. So here's what Bessel functions of the first kind look like if you want to go read more about them. So we're specifically looking at this J0 term, which just has a functional form that looks like that. Really, there's not a ton of physical meaning here, because what happens inside that function is it's evaluating that function as a function of zeta 1 and our dimensionless radius. So that zeta 1 probably won't have a lot of great physical meaning to you, but you calculate that term inside, and then you just apply this operator. But this is another thing you can look up in the book. So we'll fairly rarely encounter these kind of problems where you have to look up the Bessel function. But here's the table, how that looks if you're so interested. Okay, so just an open question. So the constants from table 5.1 help us get approximate solutions to what equation? Yeah, it's just the heat equation. We're just solving the heat equation. We're now just including a functional form of the heat equation where the solutions in these particular instances end up looking a little bit ugly. So we have to go look up these constants given to us by people who are smarter than me that have gone through and solved all these problems. Yeah, Nimdo?
So we have different solutions because we have different boundary conditions. And so do the boundary conditions change because we assumed the thermal, what's it called, the lumped capacitance? Is that why the initial conditions change?
So the initial condition, so for these particular solutions, we're assuming that our initial condition is just constant temperature everywhere. And then our boundary conditions are no flux at the center of our system. So dt dx is equal to 0 at the center or right at the insulated edge. dTdr, if it's a radial system, is just going to be at the center of the cylinder or the sphere. And then this particular case is when you have uniform convection at the boundaries. So these solutions are applied to the heat equation only in those specific instances.
Oh, okay. So yeah, that constant T is from the lumped capacitance assumption.
Yeah, So the lumped capacitance, we avoid all this stuff. With lumped capacitance, you don't have to deal with boundary conditions at all because you don't care how temperature varies with respect to space. So you don't need boundary conditions. You don't really need the heat equation even. You're just assuming that your whole solid is all at a uniform temperature, and that by changing something, that starts to make the temperature change with time. Any other questions? I think I might stop here for today. Let's just see. Okay, so let's go a little bit further. So for Cartesian systems, we're solving the heat equation, but we're getting rid of those things, and we're ending up with a solution like that under these specific boundary conditions. The one-term approximation is just taking that first term of this infinite series. For the infinitely long cylinder, we don't care about those things, and our solution looks like this, and we can take that first term. Keep in mind that our theta star is defined like that, and this is sort of just similar for a spherical system. There's just a different functional form that you can find in the book. Okay, yeah, that's a good stopping place. All right, so remember on Wednesday to bring your computer and to dive into the last problem on homework 4. Watch the videos beforehand and just be prepared to come. It'll be to your own benefit to come prepared with specific questions.